Hi, my name is Amy Zhang, and welcome to my presentation on preparing for influenza season in the United States. This project aims to devise a set of guidelines for a medical agency that is tasked with deciding when and where to send temporary staff across the U.S. Their function is to help with the implementation of flu impact mitigating measures, and these include addressing staffing shortages during outbreaks to preventative initiatives like vaccination campaigns. Influenza, a viral respiratory illness, typically lasts 4 to 7 days, but it can be fatal in severe cases. By analyzing mortality data, we can begin to identify flu impact trends requiring our attention. Between 2009 to 2017, the U.S. experienced on average 66,906 cases of influenza mortality a year. This choropleth map illustrates the uneven concentration of flu deaths across the U.S. This distribution remains relatively stable from 2009 to 2017, as indicated by the persistence of each state's color category. However, notable changes indicate the unpredictability of influenza's impact. For example, while the national flu mortality rate declined between 2013 to 2014, a number of states in the East experienced increases in deaths, moving up a color category. If you look at the East Coast, between 2013 to 2014 on the map. These variations underscore the importance of considering state-specific circumstances in shaping the severity of flu outcomes. But for the support to be truly effective, we also need to consider timing. The below line graph here reveals a consistent overall trend, a rise and fall in deaths, with peaks typically occurring within the same bracket of months, year to year. So 2009 is a notable exception here, with an earlier and more accelerated start in the fall. This outlier raises an important question. Does the shape and timing of the overall trend line persist when viewed regionally? How uniform is the flu season in the U.S., or are there regional variations that we need to consider? In this graph, this line graph here of monthly flu deaths, we see that each of the 4 regional lines move in parallel, meaning that the flu season is largely concurrent across the U.S. Flu deaths begin rising in September, they tend to peak in January, and typically decline by May. The South and Midwest also experience a second peak in March, and the dynamic bar graph below offers another view of these trends. January is the peak month across all regions. March ranks in the top 3 for all. And the overall shape of the bar graph for each region exhibits a similar geometry. And this supports the model of a synchronous flu season that begins in the fall, peaks in the winter, and extends into spring. So instead of variations in regional timing, we can shift our focus to resource allocation questions. For example, the South has average monthly deaths in some months that exceed 2,000, unlike for the other states that fall to the left of this reference line. This regional disparity, evident in both the line and the bar graphs, prompts the question, what factors drive these differences in flu outcomes, and how should resources be allocated to address them? A closer examination of mortality trends reveals that individuals aged 65 and older bear a disproportionate burden of flu-related deaths. This area line chart illustrates that the 3 largest categories for flu deaths are all from the 65 and older age groups. The 2 pie charts, one showing population distribution and the other depicting a flu death distribution, highlight that while the 65 and older age group represented just 10% of the population, they accounted for nearly 2/3 of flu deaths between 2009 to 2017. The scatter plot here shows a strong positive correlation with the coefficient of 0.95 between the size of the elderly population and flu death counts, indicating that states with larger 65 and older populations tend to experience higher flu death counts. Given this, the question arises, should our strategy focus on the raw numbers of vulnerable residents? Raw death counts can't tell us the whole story. This version of the previous scatter plot now has its dots sized by each state's total population. We see that dots grow larger as they trend upward, suggesting that flu deaths rise with not just the 65 and older population size, but the population size overall. This doesn't undermine the utility of our age-related mortality finding. What the added dimension does is bring the question of proportion to our attention. A state like California experiences more deaths, but this might not signal the same urgency as fewer deaths in Alaska due to its smaller population to begin with. By dividing the number of deaths in a group by their population size, we get the death rate, a normalized metric that tells us how frequently flu-related deaths occur for individuals in this population set. It allows for us to make the distinction between vulnerability, the inherent uniform susceptibility of older populations, with the disparate levels of risk, individual risk, that they actually face between states. When we toggle the scatter plot so that the size of each dot is now sized to the state's death rate rather than the population size, the shift is remarkable. The pattern along the trend line seemed to flip completely, and smaller states like Alaska now emerge as far more urgent than California. And Florida, which we would have deemed as the second most in need of resources, had begun by defining urgency as population size, second here, now shows up very last in terms of urgency when determined by death rate. However, while high death rates in smaller states signal urgency, high death counts in larger states emphasize the volume of resources required. Therefore, our strategy must find a way to differentiate between healthcare systems that are under stress. This is where systemic weaknesses amplify individual risk, and those that are under strain, where surges in patient volume due to a larger vulnerable population create temporary deformations in an otherwise functional infrastructure. We developed an experimental flu severity parsing index to integrate these two flu severity paradigms, stress and strain, into a shared framework. The FSPI compares the 65 and older death rate to the overall death rate, providing a simple yet powerful diagnostic ratio to begin answering two critical questions. How much greater is the risk for older adults compared to the population at large? And how does the state's healthcare system serve both vulnerable and general populations during flu season? By using the overall death rate instead of just the under 65 death rate as the denominator, the FSPI anchors itself to systemic healthcare performance rather than exaggerating the age gap. What results is a preliminary diagnostic framework here. High FSPI values indicate that flu fatalities are more concentrated among the elderly because the numerator, the 65 and older death rate, far exceeds the denominator, the overall death rate. Low FSPI values would suggest that the 65 and older death rate is closer to the overall state death rate, meaning flu deaths are more evenly distributed across age groups. Crucially, neither a high nor a low FSPI value is inherently good or bad. High FSPI may reflect natural age-related vulnerability, but it could also indicate excessive disparity caused by a strained healthcare system during flu season. Low FSPI isn't always a sign of efficiency. A ratio approaching 1 can result from two vastly different scenarios. Both the 65 and older and overall death rates are low. This would be a high-performing system. Or both are dangerously high, a stress system struggling to support all age groups. So while we do have a paradigm now that accommodates both the urgency of Alaska and California in the same visual frame in particular, as we can see, the scatter plot for the relationship between FSPIs and 65 and older death rates alerts us to the need to interpret carefully. This wide vertical scatter along the elderly death rate y-axis hints that despite their similar relatively low FSPIs, healthcare conditions in, let's say, South Dakota are quite different from those of Maine, where the death rates are lower. So even though they are going by the FSPI, the same, their death rate conditions are quite different. This is where residuals can help. These represent deviations from the trend line. The trend line defines the maximum reasonable 65 and older death rate for a given FSPI value. That it has a negative slope is a positive finding. We expect the 65 and older death rate to be disproportionate to the overall death rate due to natural age-related factors. However, we don't want this disparity to be excessive. Therefore, it is reassuring to see that as the FSPI rises, indicating a larger disparity, the elderly death rate is at least trending downward. So the higher the residual, the darker the red, the more 65 and older deaths significantly exceed expectations. The lower the residual, the cooler the tone, reflecting states with better than expected outcomes for older populations, like Florida here. By cross-referencing residuals with FSPI values, we get a glimpse into the overall performance of each healthcare system. While the FSPI doesn't indicate how high is too high for the 65 and older death rate numerator, residuals can help to fill this gap by using the trend line as a benchmark. So, for example, Alaska's residuals reveal that its 65 and older death rate exceeds what would be expected for its FSPI. Its moderate FSPI, coupling it with that, we can infer that Alaska's overall death rate is similarly elevated, indicating that the issue for the state is not isolated to elderly care. In contrast, Arkansas, which also has a moderate FSPI, shows a 65 and older death rate much closer to the expected value. So while we would still flag the state for more system-wide initiatives, this suggests that in Arkansas, we should allocate a larger proportion of resources to elderly-specific care than we would suggest for Alaska. There are, of course, major limitations to our experimental FSPI model. First, there's the assumption that the national trend line represents an ideal benchmark. Meanwhile, the U.S. healthcare system might be far from optimal globally. Second, the 9-year dataset is too brief to capture long-term trends or anomalies. And third, key contextual factors such as health insurance coverage, doctors per capita, and state-level response systems remain unexamined. But to this last point, the FSPI and residuals turn out to be foundational metrics that can help us navigate the future research trajectories required. By using FSPI ratios and residuals, we can group states into meaningful cross-regional clusters based on shared characteristics in flu-related challenges. These informed random samples, based on dividing the national FSPI range by 3, serve as statistical subpopulations for in-depth research. Each query cluster focuses on a different aspect of the flu impact dynamic. Query cluster 1, high FSPI states with low positive residuals. This combination emphasizes states whose primary challenge revolves around elderly care. Notably, the majority in this group fall to the right of the 0 residual mark. This is a translation of the negative trend line in the previous scatter plot. And this means that their elderly death rates are not just high, but disproportionately so. What these states have in common is that many rank among the largest in population size in the US, with significant metropolitan concentrations. New York City in New York, Los Angeles in California, Atlanta in Georgia. We can use this cluster to focus on the complex interplay between strain and urban centers, moving us beyond a simple correlation with population size alone. It sets the stage for a deeper exploration into how healthcare infrastructure, urban population density and localized distributions of aging populations collectively shape flu impact challenges. Query cluster 2, low FSPI states, these are mid FSPI states. This is an intriguing and diverse cluster. It contains what may represent the two most extreme cases of healthcare system resilience in the US. Alaska, an outlier with an extremely high residual, contrasts sharply with Florida, one of the nation's highest performing states. In between these extremes, we find a variety of mid to large population states. Strikingly, they are nearly evenly split to the left and to the right of the zero residual reference line. This suggests an opportunity to develop a finer understanding of the stress-strain spectrum and tipping points. Also, relative to query cluster 1, this cluster's FSPIs are lower, so this indicates that flu factors tend to be less age concentrated. These states offer an opportunity to analyze other vulnerabilities, such as socioeconomic factors, race, and urban-rural dynamics. These factors are inherently complex and varied, so having a focused subset of states provides a manageable starting point. And finally, query cluster 3, these are the low FSPI states, and these states are among the smallest population states in the US, and many are predominantly rural. Compared to other clusters, their flu outcomes are the least age-driven, low FSPI. They're also more evenly dispersed horizontally across the residual axis. It's something that is more apparent when you look at the whole relative to the others and excluding the outlier in query cluster 2. And this indicates a balanced variability in their outcomes. Here we have a unique opportunity to investigate the specific challenges and priorities of rural healthcare systems. There is an intriguing outlier, Washington, D.C., which despite its urban setting may share healthcare delivery challenges more commonly associated with rural areas. Understanding stressed rural system patterns in non-rural settings, such as D.C., could yield critical insights for addressing urban healthcare in smaller jurisdictions, contexts that fall outside of query cluster 1's conventional metropolitan profiles. As such, DC should remain integral to the rural research themes explored within this query cluster. So in conclusion, for this project, we've analyzed influenza mortality trends over time and across US census regions. This culminated in the development of the Flu Severity Parsing Index. This index, combined with the counterpart Residuals, has enabled us to identify and propose query clusters for further research. These clusters provide a framework for understanding the nuanced challenges faced by different states and regions, paving the way for a more targeted, data-driven approach to flu preparedness. Thank you.